Today, we're going to be considering the Kerala School of Mathematics. This is a collection of Indian mathematicians, beginning with Madhava, probably about the 1360s, going all the way until the early 17th century. The main contributors we'll consider are going to be Madhava, Nilakantha, and Deva. We will also take a detour towards the end to talk about how the mathematics done in Kerala may have reached back into Europe. And one other interesting consideration that we could have made but won't for the sake of time is how the mathematics of India were likely shaped by the surrounding mathematics of various Arabic scholars and various Greek scholars that either directly or indirectly through the Arabic scholars transmitted their knowledge. So Madhava is generally considered the founder of the Kerala school, and many results are attributed to him. It's not at all clear that these results are in fact his, though they may be. Neugebauer certainly makes many interesting assertions about the Kerala School of Mathematics, and his article at this point on the Kerala School is quite old. He's really very forward-looking in his article, but he talks more about what is not known than what is known. The main work we're going to spend a lot of time talking about is going to be the Tantra Samgraha, and more particularly the Yuktibhasa. Nilakantha was a disciple of Madhava. There was a sort of mysticism surrounding numbers, very similar to Greek number mysticism. Nilakantha compiled a list of results, and he wrote them into verse form. And we're going to spend a second, and we'll even hear some of these verses as they might have been spoken or sung. And so they really have the same poetic structure as a lot of the religious works of the time, like the Vedas and the Bhagavad Gita, though the native language of Kerala is Malayalam and not Sanskrit. But many of these texts appear in both Malayalam and Sanskrit. The Yuktibhasa is interesting and unique because it offers somewhat rigorous proofs, or at least the sketch of what might be considered a rigorous proof for many of Madhava's results. This work is really a commentary on the Tantra Samgraha, and it's written much later than most of these results. But it will really attempt to do is explore one really profound result that crops up again and again in mathematics across cultures. And we'll look at particularly how Deva outlined the proof that he attributes to Nilakantha, and the result, of course, Nilakantha attributes to Madhava. And it is possible that the proof itself stems from Madhava. And we'll see some elements of rudimentary induction, along with some sort of methodologies of approximations and direct proof, which are interesting. Slide 2. One really sort of powerful and interesting thing to consider is that the Indians had no clear notion of calculus. They certainly had no fundamental theory of calculus. What they really considered was sort of an idea that's more akin to what algebraists would now call formal power series. They derived these power series, but they didn't do it with eyes towards calculus or towards limits, though they seem to have some rudimentary conception of a limit. And they certainly didn't formulate a fundamental theorem of calculus. So they didn't have a good way to relate the power series of sine and cosine, though when you write one out, you can certainly see that there seems to be a non-trivial relationship too. The Tantra Samgraha was written in 1501 by Nilakantha Somayaji. So we've got a nice picture of it written in, I believe that's Malayalam. It's even still today often preserved and written in this form. You can see it's written in a collection of verses, and they're usually about astronomical and mathematical objects. One of the really compelling things to note here is that astronomy and an understanding of physics seems to have been the main driver for these mathematical derivations. Later commentaries will largely be what we draw on, though, because they contain much more complete mathematics. And the two that are of particular importance are the Tantra Samgraha Vyakya and the Yuktibasa. And mostly we'll be looking at the latter and not the former. Although the article that I pulled the outline of the proof from for the result we'll be looking at drew from all extant sources that were known at the time, and that was written fairly recently, in the 90s at least. Madhava's cosine series is stated clearly in verses 2.442 and 2.443 in the Yuktidipika commentary, which is part of the Tetrasamgraha Vyakya, and that's by one of Nilakantha's disciples, Sankaracharya. And here we have a really nice translation. Multiply the square of the arc by the unit, and take the result of repeating that any number of times. Divide by the square of the successive even numbers decreased by that number, and multiplied by the square of the radius. But the first term is divided by twice the radius. Place the successive results so obtain one below the other, and subtract each from the one above. These together give the Sara as collected together in the verse beginning with Stena Street. So pretty much all of this, including the parenthetical text appears, although it's likely that the parenthetical text was only intended for clarity and not to be read. It doesn't fit poetic meter. It's even somewhat poetic in English. It's kind of interesting. Now, the particular result that I'm going to spend some time with here is this one, because this series, in fact, in recent years, the series up until the 20th century was most often called the Leibniz series, because Leibniz derives the series in a totally distinct way. The series is come to be known as the Madhava-Leibniz series in many modern texts now, to honor Madhava's and the many Indian mathematicians' contributions, and the ambiguity of whether this series was originally discovered by Leibniz or not. We'll hear a recitation of the verse containing the description of the series. We won't listen to much more than that, because otherwise we would be listening to a very verbose outlining of how to derive parts of the series.
Nihate Rupahृते Vyasasagaraabhihate Trisharadi Vishamasankhya Bhaktam Rinam Swam Prithak-kramat Kuryat.
The really nice thing you get out of this series, and the nice thing that was noted in the Nilakantha's results, was that you get an error term for this series. And particularly this error term shows you what poor convergence you have. So you just look, each of the terms are the alternating odd reciprocals. And let's say we want to be accurate in the, to 10 decimal places. Well, then what we really are going to need is roughly 5 times 10 to the 9th minus a half. So roughly 5 billion terms of the series. And that's just an insanely slow convergence. You can see the convergence sort of pictured to the right. It looks better than it is, honestly. It's pretty poor. So the way that a lot of modern mathematicians would derive this series would be to consider the arctan of 1, and then sort of rewrite that as an integral, and then express that integral as the partial sum of a geometric series, with the substitution that z equals negative x squared for our geometric series. And that works, and that's a very quick and nice and precise way to obtain the series. This, of course, is not how Nilakantha would have considered this, because he didn't have the tools of calculus. But what he did have at this point was a very well-developed theory of circular geometry, but also a theory of power series. And I'm not going to spend a lot of time deriving the geometry, because I could spend the entirety of the presentation really just explaining the way in which they understood this relatively simple diagram. There is sort of a difference here, though, which I will point out, which is that they preferred to do what would now often be known as total rectification of a circle or of a curved object, which is different from like quadrature, which is the more classical way to obtain approximations of increasing goodness for a curved figure. And so what Giustadeva does is he says, if we look at an eighth the arc of a circle, that is going to be roughly an angle pi over 4. And he says, what we're sort of looking at is these points PR minus 1 to PR, and we're taking a limit as we collect up those points. We're putting them over basically the length of the 1 plus the radius squared. So, and this is going to give us this. So we can see that this is in some way like this arctan series. This is somehow analogous to exactly what I was talking about in the prior series. So this is somehow intuitive approach to that. But here we've constructed it geometrically, like wholly geometrically. And you can also see there's this notion of limits inherent here, because he even does some calculations where in his commentary where he takes n to be a certain fixed quantity and says, okay, this is giving us an approximation, and then this is giving us an approximation. And he says, really, we could take an approximation as good as we want, so we can make n as big as we want. So what he does is, after establishing the geometric fact from the last slide, he uses a geometric series. He then does iterative substitution. So he just uses the straight up standard geometric series and substitutes negative x for x. And he then does this sort of really nice iterative substitution because he notes that if he does the right sort of factoring, you have the same geometric series living in the geometric series. And he does this a couple of times. And there are some potential problems with this, right? There's a modern problem of convergence. Like, this is in no way guaranteed to converge, and a lot of the work he's done here would be considered sort of silly by modern standards without the right balance on x, right? But entertainingly enough, you look at a modern book on formal power series or Q series or whatever, they just say, assume Q as the right domain so that this is absolutely convergent. And certainly if we take the absolute value of x strictly less than 1, this should work, and it will. Then we will construct the second lemma. And what we're doing here is we're taking this partial sum approximation for the sum of n integers to some power p. P is not per se prime, it's just some number. And this approximation holds for n sufficiently large. Now, the first observation that Giustadeva makes is if we multiply n by Sn p minus 1, so we've just reduced our exponent by 1, it's equal to the sum of these partial sums. So n times Sn to the p minus 1 is equal to the partial sum of this other collection of series. So why is this nice, or how is this going to be useful? We're actually going to combine it with the previous result. This is where we're going to make use of our inductive step. He then notes with some algebraic manipulation that you can take everything in there up to Sn minus 1 to the p minus 1, and all of that's just approximately Sn to the p over p. So this is basically your standard inductive hypothesis. So now he's made the inductive hypothesis, and he looks at his previous notation. Now, in the previous notation, the things are actually equal. Like, you do some algebra and you can show that they're actually equal. In this, what he does is he takes that and he substitutes in the inductive hypothesis for all the terms following Sn to the p. If we simplify the right-hand side and substitute using our previous assumptions, then we're going to get the desired result. So we can see I've written the algebra out there, so there's nothing too remarkable there. I mean, this takes like the third line of the slide and the second line of the slide and sort of combines them in 2 steps. Now, the Yuktibasa again demonstrates this for p equals 2, p equals 3, and then supposes the general result, which is actually very, very close to the modern notion of induction. We have a base case, and then we assume the general case, and then we work forward using the inductive assumption to show that if it holds for n, it holds for n plus 1. So interestingly, at the same time, Alhazen, an Arabic scholar, shows the identical result, but shows it completely geometrically. So he constructs the same series of results, and they are him and Nilakantha are contemporaries, and so it's quite possible that Nilakantha knew of his result. Though, since Jayadeva gives a totally different treatment and construction of this result, it's unlikely that it influenced his understanding of it. Although it's also, again, it is possible that all of this was orally passed down all the way from Madhava. So we can expand our expression for pi over 4 in a geometric series as follows. We take the original geometric expression that we had from slide 6 in this series of slides. We then expand it out using the geometric series. So that's all we've done. And now I'm just going to do a substitution, because if you looked at that slide closely, you would see delta is approximately 1 over n. We take n to be larger, it pushes the points closer together because we've got a finite portion of a circle of fixed radius. Now we have this collection of sums, and what we do is for each of those sums from r equals 1 to n, and since we know we're going to let our limit tend to infinity, n is going to eventually be quite large, so we apply the result from lemma 2. And so this gives us exactly what we're looking for. We get the n terms canceling in every single one of these, and all we're left with is the denominators. And so we have this nice alternating series, which proves our result. So Nilakantha really spells out that he's aware any finite truncation of this series in rational numbers is only an approximation. And in the Arabhataya Bhāsya, he writes, if the diameter measured using some unit of measure were commensurable with that unit, then the circumference would not likewise allow itself to be measured by means of the same unit. So likewise, in the case where the circumference is measurable by some unit, then the diameter cannot be measured using the same unit. This is interesting because he realizes that you can get rational approximations for numbers, and that these rational approximations somehow, at the end of the day, fail to capture irrational numbers. So it's almost the beginning of modern irrational number theory, which we don't really see again until Legendre, Dirichlet, Dedekind. I mean, it's quite a while before that realization is made in Europe, certainly for numbers like pi and e. So they're suspected to be irrational. The only thing that people can prove to be irrational for a very long time is nth roots of non-nth powers. Another interesting thing to note is he was aware of the convergence, he noted it, and he actually used what we would consider modern techniques of convergence acceleration to construct series that gave much better convergence in very few terms. I would go through one of those, but it's going to be a matter of time at this point, because I also want to spend some time on some of the history, math history's great scholars' conjectures, which I think are worth at least addressing or considering. Katz maintains there's no evidence that Indian mathematicians influenced European math. I think that Neugebauer maintains that there's no influence, and there wasn't really. There was no evidence of influence of Indian math on European mathematics. He does maintain an open mind. He just says that there's no evidence. And when he's writing that article, I think it's pretty fair to say that things like the internet and the availability of codices from around the world at the touch of a button were simply not there. He is very generous and forward-looking in his analysis of what he comes across. And he does admit that there is a possibility. Now, Katz, on the other hand, wrote an article, Ideas of Calculus in Islam in India, And in it, he proposes that Leibniz and Newton surely derived calculus on their own. And very few people are going to dispute this. But it is not unlikely that some channels, such as Jesuit missionaries, varied knowledge from Indian mathematicians to Fermat, Roberval, so on, and in turn influenced the modern development of calculus. In fact, not only is it unlikely, in many cases it's very likely. Like Francis Xavier goes to Kerala at the height of the Kerala School of Mathematics, and he would have been, as a Jesuit missionary, mathematically literate to a greater or lesser degree. And the Jesuits did something very different from other missionaries. They learned the local language. So he would have been able to at least converse sensibly in Malayalam, if not Sanskrit as well. And he would have probably recognized mathematics, and he would have probably copied it, and he would have probably brought it back. And an underappreciated fact of the time was that monasteries usually were the places mathematicians communicated to each other. They would take letters to monasteries, monks would copy those letters, and they would send them to the relevant mathematicians. And they'd usually archive a copy too. Now, I even made a request for some of the archived works from the Jesuit libraries that would be likely to house them. The collected personal works of Francis Xavier, considerably greater than the published works of Francis Xavier, are not publicly viewable or available. I did try to communicate with those librarians, and they simply either are not interested in communicating or are too busy because they never got back to me. And I tried to communicate with several different people. It's also possible too, because you become this librarian by papal appointment and you become like an archbishop as the result. Maybe they're busy or important people and simply don't have time to answer all the crazy emails that come to them. That really concludes my presentation on Indian mathematicians. Oh, I do want to make one more point, which is that another very famous 20th century mathematician is Ramanujan. And it is possible Ramanujan grows up in Tamil Nadu, which is the neighboring state to Kerala. And really, he grows up in like the Madras area. And there's a lot of trade between these areas. There's a lot of trade all over. India is extraordinarily connected for as large as it is throughout most of its history. But Ramanujan goes on to work in Q series. And Q series are really like he developed seminal ideas that totally change partition theory and revolutionize a lot of modern calculus. And they are the natural extension of historical mathematics coming out of the Kerala school. And they were well in advance of where European mathematicians studying power series and those same things were at the time. And it's possible that he came across some of these traditional Indian texts and that he then worked to advance them or came up with new results. And that's his results, in fact, were built on. And I honestly, I think that's kind of beautiful because you see this Indian tradition that created yet another really great Indian mathematician feeding into that European tradition, so that you see this beautiful dialogue of mathematics that has moved all around the world. Because it's likely that the Greeks, who had some faint notion of calculus and possibly very little notion of power series, but notions of other things like quadrature, transmitted that knowledge to Arabic scholars, who transmitted that knowledge to Indian scholars, who then may have transmitted that knowledge back to European scholars, who then rederive calculus. And I think that's an incredible journey and an incredible conversation that has gone on for 2 millennia to preserve some of humanity's best work.